The Steel Structures Education Foundation is an organization established to foster increased awareness of steel as a building material and to expand the knowledge and understanding of the use of steel in construction. Years ago, when we looked ahead to the urban landscape of the 21st century, we imagined a skyline dominated by multi-story buildings. That future is now here. But the modern urban environment has an unexpected number of single-story structures, and many of those are framed in steel. In this program, we look at the design and construction of the single-story building. We examine the vertical and lateral loads that these buildings must carry and the structural systems used to transfer the loads to building foundations. We start with the loads. In Canada, one of the most severe loading conditions to consider is snow. Snow can pile up locally, especially where there are changes in roof elevation, as this model simulation demonstrates. And when rain is trapped in the snow, the load substantially increases. It's not surprising that structural failure in building roofs is most frequent under snow load conditions, and rain must also be considered as a separate load source. Designing for rain loading is often compounded by local bylaws. Some municipalities restrict the volume of runoff from building roofs. In these cases, the design must allow for the extra load of retained water, and the load is not always evenly distributed. Roof frame deflection can cause the rainwater to pond in low areas, causing locally heavier loads. Roof stiffness to avoid deflection and drains at low points are therefore two important design considerations. To carry roof loads due to snow and rain, sheet steel is the first line of defense. The designer chooses one of a number of standard roof deck profiles based on deck span, sheet steel thickness, and anticipated roof load. A coil of sheet steel is roll-formed into the deck profile selected, and a flying shear cuts it into suitable lengths. Open-web steel joists, simply called joists, support the roof deck. Each manufacturer uses its own proprietary joist design, selecting components that comply with the specified performance criteria. Assembly line fabrication reduces overall costs. In areas where there are extra loads from deeper snow, designers will often call for a joist with a larger capacity to support the additional weight and place the joists at the normal spacing. But the production of these few heavier-duty joists is apart from the assembly line and can drive up costs. It may therefore be more cost-effective to use the same joist design that's in the rest of the roof and place them closer together where necessary to increase load capacity. Reducing joist spacing also reduces the deck span, thus increasing the load capacity of the roof deck. This may also avoid the need to adjust deck strength in areas of heavier loading. The next element in the steel framing of a one-story building is the girders. These are the primary supports for the joists. They are often cantilever girders, also known as Gerber girders, named after the designer Heinrich Gerber. More than a century ago, he used cantilever girders in European bridges to achieve the benefits of continuous girders, with the structure remaining statically determinate. In buildings, Gerber girders are continuous over adjacent columns, with simple span drop-in segments attached to the ends of the cantilevers. This continuity over the supports reduces deflections and simplifies connections. The system also derives significant economic benefits from material savings, easier fabrication in the shop, and faster construction in the field. There is one critical fact in the consideration of this design. The maximum bending moment under uniformly distributed loads frequently occurs over interior columns. This point of maximum negative moment coincides with the maximum shear force in the girder. Therefore, stability of the girder column joint is an essential factor in the design. When roof loads are low, as they are most of the year, the assembly usually remains stable. However, as loads increase, there is a tendency for the bottom flange of the girder and the top of the column to move laterally. This can create instability. The solution is in the framing details that transfer loads to the girder top flange from the joists. good practice dictates that there will be a joist at or near the column. An extension of the joist bottom cord may be used to tie and stabilize the girder bottom flange, thus stabilizing the top of the column. Alternatively, stiffeners on the girder web above the column may be sized to provide column continuity, joint stiffness, and joint stability. In fact, designers will often combine these two systems for additional safety. Continuing our look at the single-story steel structure, the next step is the columns, interior and exterior. We start with interior. These columns are normally designed as axially loaded pin-ended members that are laterally unsupported along their length. Their design length is approximately the same on both principal axes. This symmetry, combined with compression-only loading, usually makes square hollow structural sections the most economical choice. Exterior columns often involve a different set of design criteria. First of all, there are wind loads to consider. Wind produces loads on both the windward and leeward faces of the building, as well as uplift forces on the roof. Sometimes building walls are capable of spanning from the foundation to the top of the building. This distributes wind loads in more or less equal shares to the roof level and the foundation. In these cases, the exterior columns can function primarily as axially loaded members. However, much more frequently, the wall consists of cladding that is attached to the exterior columns. Wind loads on the cladding are locally transferred to secondary framing members called girts, and from the girts to the exterior columns. Girts are used in a horizontal plane with sag rods to support them temporarily, and with their spacing usually determined by the load capacity of the cladding panels. The columns then must support both wind loads on the wall applied through the girts and axial loads from the roof. In many cases, girts are attached to columns on their outer flanges. These horizontal loads may reverse with the wind direction, which makes it necessary to consider stability of the inner column flange. To supply both axial load capacity and bending capacity, designers will usually choose a column with greater strength on its primary axis, such as a wide flange column section. The spacing between primary exterior columns is usually a reflection of the interior column grid and may be too great for economical spans of the wind girts. Secondary columns placed between the primary columns will reduce the girt span. These additional columns are known as wind columns. In fact, they might well be called wind beams because their major function is to resist horizontal loads from the wind girts. These are the main framing elements in the construction of a single-story building: the roof deck, joists and girders, interior and exterior columns, girts and wind columns. Now, let's see how these framing elements work together in tandem with the bracing to provide overall building stability under gravity loads and to resist horizontal loads from wind or earthquake. Loads at the bottom of exterior columns are transferred directly to the foundations. Loads at the top of exterior columns must be resisted at the roof level. The designer must find a way to distribute these horizontal loads to bracing elements, which quite frequently can only be accommodated along the perimeter of the structure. How do designers transfer loads to these isolated elements? Most often, they use the roof as a structural diaphragm. A steel roof deck with joists acting as stiffening elements forms the structural diaphragm, which must have the capacity, both overall and internally between adjacent elements, to transfer forces across its width. In addition, the boundary of each diaphragm must have sufficient connections to transfer forces through bracing elements to the foundations. Sometimes a steel deck diaphragm alone may not be capable of distributing forces applied on the building. In such cases, a bracing system in the plane of the roof supplements the diaphragm locally where stresses are high, or may even replace the deck diaphragm. Now that we have seen the loads and the components that support them, let's look more closely at actual site construction. The building contractor constructs footings to plans and specifications, complete with anchor bolts. The shop fabricated columns with base plates are erected and shimmed to the correct elevation, ready for grouting. As an alternative, leveling plates can be installed and grouted before the columns are erected. After several columns have been bolted down, the cantilever segments of the girder system are erected. Drop-in spans complete the lines of the primary framing elements. Usually a tie joist, that is, a special joist with a bottom chord extension, is placed on the column grid lines. Erectors use this bottom chord extension, along with plumbing cables, to plumb the frame. This is the point in the girder where we see the large negative bending moment discussed earlier. To stabilize the joint, we connect the joist bottom chord, ensuring stability of the girder bottom flange and the top of the column. After girders are placed and stabilized by tie joists and plumbing cables, bundles of open web steel joists can be placed on the frame. They are then spread to the specified spacing and attached to the girders by bolting or welding. Bridging is then installed to brace the joists. With joists and girders complete, the third element in the roof structure can be laid, the steel roof deck. The erector places panels side by side on the joist top chords and welds or mechanically attaches each to the joists. Side seams are connected for vertical load carrying capacity, with additional connections for roof diaphragm capacity if required. Now, let's take a closer look at the building wall. There are many different wall systems to use. Wall panels may be factory manufactured, and these large elements are shipped to the site. The wall may also be manufactured in the field, beginning with a liner sheet attached to the structural girt system, followed by subgirts, insulation, and finally, the exterior finish panels. As the wall cladding is installed, one other construction process is underway, the completion of the roof system. One common roof system calls for insulation to be placed on the roof deck and connected to the deck to keep it in place. The thickness of the insulation varies with the temperature requirements of the occupants and the energy conservation philosophy of the building owner. The waterproof coating on top of the insulation is usually several layers of asphalt paper bonded by hot asphalt and protected by a layer of fine gravel. The basic structure of the building is now complete and work on the interior begins. In this program, we have examined the elements used in the construction of a single-story building. We have seen how each framing element plays a key role in transferring vertical and lateral loads to the foundation, and we have followed the assembly of these elements into a cohesive design. The final structure ensures the stability of each framing component, as well as the overall stability of the building. As the frame is enclosed with its architectural finishes, a new workspace is complete. Each structural element complements the others, often acting in a dual capacity, and the architectural finishes may also contribute a structural function. We have met the engineering challenges of a single-story building. We have produced a highly optimized yet repetitive and economical design, and another functional, attractive building has been added to our modern urban environment.